Welcome back to Game Theory 101. I'm William Spaniel. Today's topic is screening games. This will be our first time solving for perfect Bayesian equilibria after having defined that in the last lecture. And in fact, you may recall that we left off last time discussing two different types of games that we're going to solve for in this unit: screening games and signaling games. Screening games are situations where uninformed actors move first, whereas signaling games are situations where informed actors moved first. Remember that this unit is on sequential games of incomplete information, so players are taking turns moving and seeing what others have done previously in environments where at least one party has some sort of asymmetric information about the payoffs associated with the various outcomes of a game. Screening games are a lot easier to solve for, and that's why we're starting with them in this lecture. So let's get to it. Let's see a game of incomplete information. Games of incomplete information tend to start out in the same way. It's a move by nature. Nature is an autonomous actor. It's not strategic. It behaves randomly in a way that's defined by the parameters of the game. Here, nature is either choosing player 2 to be weak or player 2 to be strong. And specifically, it's going to choose weak with probability P and strong with probability 1 minus P. P and 1 minus P are the prior beliefs that player 1 is going to have about player 2's type. So if we flesh out the rest of this game, it's country 1 and country 2 in some sort of crisis over a good that they both want. Player 1 can either escalate the dispute or quit, and if player 1 escalates, then player 2 can either fight over the good or concede. You'll notice that after nature makes its move, we have a dashed line connecting player 1's choices. This is reflecting the fact that player 1 is in the dark. He doesn't know whether player 2 is weak or strong. He just has that prior belief of P and 1 minus P over those two different outcomes. In contrast, player 2 has complete information. Only player 1 has incomplete information. Player 2 knows whether she's weak or she's strong, so there is no corresponding dashed line. To fill out the rest of the payoffs here, if player 1 quits, it doesn't matter whether player 2 was weak or strong. Player 2 is going to capture the entire good and get a payoff of 1, whereas player 1 is going to receive nothing at all. If player 1 escalates, now player 2 has to make a move. She'll either fight or concede. If she concedes, once again, payoffs are not a function of what nature drew earlier. Player 1 will capture the entire good for himself, and player 2 will receive a payoff of 0. The types matter if player 2 fights. If player 2 is weak and fights, then we're on the very left edge of the game tree, and player 1 will receive a payoff of 0.7. He's doing very well for himself in this war because player 2 is weak, whereas player 2 is suffering quite a bit. She's receiving a payoff of negative 0.1. The reverse is going to be true if player 2 is strong. If player 2 is strong and she fights, well, now player 1 is getting a negative payoff, negative 0.2, and player 2 is doing quite well for herself. She's getting a payoff of 0.8. So this is the game. Let's go ahead and solve this, and let's see why screening games, situations where the uninformed actor is moving first, is easier to solve for. Let's see why that's the case. Well, think about what player 2 has to do. When player 2 makes her move, she knows what has happened previously. She knows what player 1 has done, and she knows her own type. There's nothing new to learn over the course of the game. So she has a very simple optimization problem in both of those cases. She can look at her payoff for fighting, and she can look at her payoff for conceding, and she can see which one's bigger. Essentially, all player 2 has to do is apply backward induction, just like what we would do for complete information games. So let's look at the weak side. If player 2 fights, she receives a payoff of negative 0.1. If she concedes, she receives a payoff of 0. 0 is better than a payoff of negative 0.1, so she should concede in this case. What about on the other side? Well, if she fights, she gets a payoff of 0.8 here. If she concedes, she gets a payoff of 0. 0.8 is larger than 0, so she should fight. So that allows us to simplify the game tree, again, just as we would in a game of complete information. So weak type is going to concede if player 1 escalates, and the strong type will fight. Thinking about player 1's strategy is a little bit more complicated. Now player 1 has to think about what's going to happen in the future if he escalates, and he doesn't actually know for sure whether player 2 is going to concede or fight. He just has a prior belief, and that prior belief is going to be enough to allow him to figure out exactly what he should do. But there's actually something simpler we can calculate first. We need to compare his payoff for escalation versus his payoff for quitting, and his payoff for quitting is very straightforward. It doesn't matter what player 2's type is. If she's weak or she's strong, player 1 is still going to receive a payoff of 0. It doesn't matter whether player 1 is going to be facing a weak type or a strong type of player 2 in that case. However, if player 1 chooses to escalate, now the types matter. But it's still relatively easy for player 1 to figure out what he should do, and we can get that by calculating the payoff for escalation. If player 1 escalates, then with probability P, player 2 will actually be a weak type and choose to concede. In that case, he gets a payoff of 1. With probability 1 minus P, player 2 is going to be a strong type who will choose to fight him. He'll get a payoff of negative 0.2 in that case. So we can calculate those, sum them together, and we get an expected payoff for escalation for player 1, which is going to be 1.2p minus 0.2. So if we want to figure out whether escalating is better than quitting, all we have to do is compare those two payoffs. And we're going to do that now. To figure out when escalating is better, we need to take the utility for escalation and set that greater than the utility for quitting. That gives us 1.2p minus 0.2 greater than 0. Do a little bit of rearranging and solve for p, and you get p greater than 1/6. So that is saying that if player 1's belief that player 2 is weak is greater than 1/6, then player 1 prefers to escalate. And analogously, if we flip that inequality, we figure out when player 1 prefers quitting, and obviously that's going to be when p is less than 1/6. We can now put all of this together. If you remember back to last time, this was our definition of perfect Bayesian equilibrium, and specifically we need a set of strategies and beliefs. So we figured out all of that. The beliefs part is actually straightforward. We don't have to do any sort of extra calculation for that because there's no updating in this screening game. It's just a prior belief. So if we put everything together, the perfect Bayesian equilibrium is going to be a function of that prior belief. This is why we care so much about beliefs in Bayesian games. It's because it drives what happens in equilibrium. So if p is greater than 1/6, then player 1 is going to escalate, and player 2 will concede if weak and fight if strong. So that takes care of the strategies part of the perfect Bayesian equilibrium. The remaining thing is to talk about that belief. But again, like I said, player 1 doesn't have to update his belief throughout the game. So player 1's belief is simply that player 2 is weak with probability P and nothing more. You'll also notice that we don't have a belief for player 2 here, and that's because player 2 has complete information. So there are no beliefs for player 2 to worry about. Meanwhile, if P is less than 1/6, then something different happens in equilibrium. Player 1 quits, and player 2 concedes if weak and fights if strong, so that part hasn't changed. It's just what player 1 is going to do. And also, player 1's belief hasn't changed either. Player 1's belief that player 2 is weak remains probability P. The last thing I want to talk about before we end today is why we call these things screening games. So if we go back to this game tree, what player 1 has the option of doing is escalating to screen out types or quitting to not screen out types. That is, if player 1 escalates, then the weak type is going to concede the issue, and the strong type is going to fight. So it elicits different behavior out of player 2. It screens or filters out one type to do one thing, and forces the other type to do another thing. It may not be as apparent why we would still call this a screening game if player 1 quits ahead of time. Because if player 1 quits, then there's no screening behaviors following that. It's just the end of the game. But this would still be called a screening game because player 1 is declining the option to try to screen out player 2's types. All right, that wraps up this lecture on screening games. Hope you enjoyed it, and hope to see you next time. Take care.